Okay, I think it's a past official start time. Are there any questions right now about anything? So right now I'm looking at what I'm using as kind of the beginning, making your exam. And your exam will be a lot like this. So number one, okay, so remember to go back, make sure at least you know where to find the stuff about the electromagnetic spectrum on PowerPoint. Remember that it goes from radio, and you've got, well, I mean, you've got it in your PowerPoint, but microwave, which some people categorize as radio. Then you have infrared, IR. You've got visible, part that we can see. You've got ultraviolet, UV. You've got X-rays. And you've got gamma rays. So the wavelengths start off very long, and they get shorter and 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 shorter. So as we go from, say, radio to gamma rays, the wavelength decreases, frequency increases, energy increases. Gamma rays are very energetic, radio waves not so much, and then it goes along in between in order. What about speed of light? What does that do? Constant. So this velocity of light is equal to c equals 3 times 10 to the 8th meters per second in a vacuum. Okay, in a vacuum, that is. Probably a few questions that are along these lines. So number one is, number two is also about the electromagnetic spectrum. Number three has to do with something we talked about over and over. Where does something appear up there? Why is it where it is up there on the periodic table? What's the main difference between hydrogen and helium, for example? Okay, 4 has you rubbing materials together. So you've got that electrostatic series where we can look on it, you rub two things together. We know which one on that list was gain electrons, which one would lose electrons. We saw that wool was higher on the list than rubber balloon and PVC pipe. So we know if we rub either one of those with the wool, they'll become negative. They'll take electrons away from the wool. But the PVC pipe was lower on the list than rubber balloon. So if we rub a rubber balloon with PVC pipe, then we know that the rubber balloon will lose electrons to the PVC pipe. Also, it's the electrons that move around, not the protons. We don't change the number of protons in things that we rub together. We change the number of electrons. The one that gains electrons becomes negative. The one that loses electrons becomes positive because there's not enough electrons to balance protons. So either if it's negative, it has an excess of electrons, not a deficit of protons, because it already had the same number of protons, didn't lose any protons or gain any protons. So it becomes negative, it has an excess of electrons. If it becomes positive, then it has a deficit of electrons. That's number 4. Number 5 is all about a ball thrown in the air. You throw it up, and at the very, very top, for just an incredibly small fraction of a second, its velocity becomes 0. But the acceleration is not 0 because acceleration is not equal to velocity over time. It's equal to change in velocity over change in time. And on Earth, it's going to be 10 meters per second squared, okay? It's actually 9.80, but we rounded up to 10 so we can do the math in our head easier. Okay, then, so it's thrown up in the air, reaches its top point. The velocity could be 0. The acceleration is not going to be 0. And there is going to be a net force because it's still accelerating. There is a net force of gravity. There's no other force acting on it that's worth mentioning. I mean, see people who say, well, oh, it's got a little bit of a buoyant force because air is a fluid. Well, that's so small that we don't even bother with it. 6 is also about a ball thrown in the air. 7 has to do with static friction and kinetic friction. Remember that something just sitting there, this stapler right here. See, right now, there's no static friction acting on that stapler, right? Static friction only pops up when I start to try to move it, and then static friction will be there, and it'll oppose the push. So it'll be equal to whatever push I give it until the push I give it is able to overcome the static frictional force. And then we got to deal with a thing called kinetic friction. That's the friction we run into when we've got the thing in motion. So if we push with a velocity, we make the object go constantly across, then that means the push force and the kinetic frictional force are equal. If our push force was a little bit greater, then we'd be accelerating it. Okay, so this has to do with the difference between definition of, for example, speed and velocity. Remember, velocity has direction associated with it. So you're traveling down the freeway at 65 miles per hour. Here comes your turnoff. You take your turnoff, you turn your steering wheel, you take your turnoff at 65 miles per hour. Your speed remains constant, 65 miles per hour. But because you change direction, your velocity is changing. The magnitude of the velocity didn't change. The direction you're going in changed. That means the velocity changed. You've got to have a net force in order to accomplish that. That would be the force between the tires and the road. Okay, and if that net force isn't there, you're not going to be able to turn. You can turn your steering wheel back and forth all you want. You'll just keep going straight, like you do, like if you get in the snow and you don't have enough traction. You just go straight when you turn your steering wheel. So that causes, that's going to be a centrifugal force, which gives us a centrifugal acceleration. That was 8. 9. 9, you're lifting a book. So basically, remember that work equals force times this over which the force is applied. We've got, if we have it in grams, the mass in grams, we've got to switch that to kilograms. We got to remember that it's mg. We're lifting with a constant velocity. We can assume that. That means that mg, mass times acceleration due to gravity, will be the weight of the object. And if we're lifting with a constant velocity, that means the lift force will be equal to the weight of the object. And then you got the distance over which you lifted it. Okay, this one has to do with kinetic energy and potential energy and conservation of mechanical energy, not conservation of energy in general. The energy of the universe is conserved, but just, we know that we try to have something go back and forth between potential and kinetic, like our ball over here. We know that not all the energy stayed with this. But to make the math easy, we assume there's no friction. So then we can actually do the problem and say that whatever we lose in potential energy becomes the kinetic energy. So this one's a conservation of energy type problem. The total energy then will remain the same. The total mechanical energy will remain the same. We're ignoring friction. Okay, this one gives you a type of wave and asks you whether it's longitudinal, transverse, or longitudinal and transverse. Yeah. 12. You got to do a little bit of math. You got to remember the mathematical model for a wave. So, and remember, if it's a sound wave, you automatically assume that's going to be 340 meters per second, unless the problem says otherwise. None of the problems on the exam will say otherwise. So you can automatically assume it says sound wave, this is 340 meters per second. The light wave is 3 times 10 to the 8 meters per second. Excellent. Okay, this one has to do with the day we got out the tuning forks. So we're hitting them softly and hitting them hard. And then also we were looking at what was stamped on them frequency-wise and see how that corresponded with our perception of what we call pitch. Okay, this is, we talked about this. It's in the PowerPoints. It's kind of like who discovered this or who said that this was true. So it could say who said that force equals mass. Who's giving credit for first putting forth the idea that force equals mass times acceleration? Well, that'd be Newton. Okay, so it's along those lines. So we talked about it. It's in the PowerPoints, and maybe something a lot of you knew before you ever walked into class too. It's really kind of famous. Okay, this one has something to do with that eardrum experiment we had. We had a bowl. We put the saran wrap over the bowl. We put the sugar on top of it. We held a tuning fork nearby. Eardrum model. Okay, this one again goes back to the day we had the tuning forks and we looked at the different frequencies stamped on them. And so how that corresponded to what we perceived as pitched. And we took one of them, hit it softly, hit it hard. What were we supposed to at least experience that day with when it came to the tuning forks? Okay, this one, there's no numbers associated with it, but you got to understand this equation again. It's more like if we double something, what happens to this other thing? This one has to do with acceleration due to gravity. Yeah, you drop something and it makes 4 statements about that object that's falling towards the earth. One of them is true, 3 of them are not true. 19, it basically has 2 waves. Yeah, it shows you like, you know, it has 2 pictures like this. Okay, and it makes some statement about the 2 waves, wave A and wave B, which one has the longer wavelength, which one has the greater frequency. They're both in air, sound waves in air, something like that. This one again has something to do with acceleration due to gravity. Drop something or throw something down. Okay, what happens to that? This one has slope. Okay, this one has, we go back to the very beginning. Remember, it's comprehensive final. So remember that we did x versus t. The slope of that, delta x over delta t, is the velocity. We do v versus t, say, I don't know, something like that, v versus t. Then the slope of this, delta v over delta t, that's the acceleration, okay? And also a flat line, a horizontal line on the distance versus time graph means the object standing still. This is a straight line on a distance versus time graph, that means the object standing still. That's false, because there's all sorts of, this is a straight line, but this object is not standing still as time goes by. It's increasing this distance away from the origin. If it's a sloping line, that means the velocity is changing, right? In other words, if you had this x versus t, and it was doing this, well, those are all different slopes. You get different velocities. So the velocity would be increasing in this case. If it was doing this, now you go from a high velocity down to a smaller velocity. Now the velocity would be decreasing. So that'd be a changing velocity if you have a slope on a, if you have a curved line on a distance versus time graph. Okay, this one has somebody doing work. It probably gives you a time in there. You're using a stopwatch with probably power in joules per second or watts is involved. That was 22. 23 shows 4 graphs. This is one of these graphs of distance versus time represents this thing. And so one of them does, the other 3 do not. So you just gotta, one of them's labeled A, B, C, and D. So you just have, and of course, Canvas will mix it up. Some of you will have C, D, B, A. Some of you have, Canvas will shuffle the answers. So it won't be A, B, C, D as the possible answers. It'll be whatever Canvas gives you. Okay, this is a lot of questions. We may not have gotten that far last semester. That's why a lot of these are from earlier stuff. So I'll give you a better idea what we'll have for more recent stuff. Okay, this one has to do with the toy car pushed, rolls for a little bit after you let go, then it comes to a stop. Okay, it's a question about that situation there. This is back to electromagnetic waves. Okay, so remember what each one of those waves does. Like radio wave, you listen to the radio. You're texting each other using microwave radio waves / radio waves. The infrared is like wavelengths that basically are connected to heat. That's why infrared glasses, you look at those, you're actually looking at the infrared rays. And those are giving off, that's the heat. That's why a hot tank engine behind a bush, with the naked eye, you can't see it. All you see is the bush. You put on those glasses, and then the heat from the engine is so much greater than the bush's temperature that you can actually see the engine behind the bush. Then you've got visible. That's the part that our eyes can see. Then you've got the ultraviolet. Okay, that's the one that gives you sunburns and skin cancer and that sort of thing. We want to avoid that. We want a little bit of it because it gives us, I think it's vitamin D. So in other words, if you're not in the sun much, they tell you to take vitamin D supplements, but you don't want too much UV. And then you've got the X-rays. That's what doctors use to see what your bones look like, that type of thing. And then you've got the gamma. That's just some of the examples for those guys. But this question is very, very easy. Okay, this is again about electromagnetic radiation. There's a chance we only got through electromagnetic radiation. I don't believe it, but there's a chance because these are heavy towards the beginning of the semester or middle of the semester. Okay, this one is about one of Newton's 3 laws. So you got the first law, an object at rest or in motion with a constant velocity will remain in that state unless acted on by a net force. You've got force equals mass times acceleration. That's the second law. The third law is that for every force, there's an equal and oppositely directed force. That's action-reaction pair. They're acting on two separate objects. The first two, we just care about forces acting on one particular object, okay? Like the apples is hanging from a tree. All we would care about is the force of gravity from the earth, and then the force of the stem holding up the apple. But if we're talking about action-reaction pair, then we're interested in the force on the apple due to the earth and the equal and opposite force on the earth due to the apple. The apple doesn't feel the force on the earth due to the apple, so that has nothing to do with the motion of the apple. Okay. This one's about an inclined plane. So remember, we had simple machines. This is already 28. Oh, I see a parallel circuit one coming up right now. So anyway, the inclined plane uses a simple machine. We had the ideal machine advantage, which you can just get by drawing a picture of it and measuring distances. And then you had the actual machine advantage, which again, we have to account for friction on that one. So the actual machine advantage is never as good as the ideal machine advantage. Also, with a simple machine, the ones we used, we gained on the force and lost on the distance. In other words, we're able to use it to apply a smaller force. We had to be willing to apply that smaller force over a greater distance. Other machines, like a catapult, apparently, you gain on the distance but lose on the force. In other words, you apply a big force over a small distance, you get a big distance but a smaller force. The one thing we never, ever, ever gain on is the energy, the work. You always have to do more work in than we get out of it. So because we got to do work against friction on the inclined plane, we have to do work against the pulley friction in the pulley. See, we had a pulley over here. Remember this one? So you got to do work against the friction. So in other words, we're going to lose on the work. We have to do more work using the machine than if we didn't use the machine. Okay. But the best one where we don't lose that much energy, I've already put them away, the crowbar. I didn't put those away. Did I put the crowbar away? Yes. Maybe that was a lot. Maybe I was in the middle of putting them away. They got interrupted. Okay, now this one here. Okay, this looks like what we did do electrostatics. We've already had electrostatic questions. Okay, 29 and 30 at least. 31. So 29, 30, 31 are all about series and parallel circuits. Remember, in a series circuit, electrons have to go through both resistances. The current's the same, and the voltages across the two resistors will add up to the voltage battery. Okay, and if one of them is bigger than the other, the one that's bigger will take up more of the voltage because it'll take more energy to get it through there. In a parallel circuit, the voltages will all be the same, but the currents going through each resistor will add up to the current coming out of the battery. And if one resistor is larger than the other, the smaller of the two will get more current. So in other words, a series, different resistances, the bigger of the two gets more voltage. In parallel, the smaller of the two will get more current. 32 has to do with what is ultimately the fate of energy, probably the single most important question, period, in that there is, period, ever. This one has to do with lists. What order, like if I say going from gamma ray to X-ray, or it could say, I'm sorry, going from not gamma ray to X-ray, it could say going from gamma ray to radio, so then you have to go back this way. What is the order of electromagnetic waves in terms of frequency or wavelength? Like in other words, which direction does the wavelength increase and which direction does the wavelength decrease? That type of thing. Energy. Okay, this has to do with police pulling you over. What are they interested in? This has to do with you getting cut off. Which way do the items, like you have to slam on your brakes, which way the items in your car go? Okay, now we're back to glass rod, silk rod, stuff like that being rubbed together. What happens? Got to go back and look at your electrostatic series. This one's also about friction. That was 37. 38 is, it's like a 5 ohm and a 10 ohm resistor connected in series. So there are four, it says a little bit more, than there are 4 statements about that situation. And one of them is correct 100%. Maybe one of, it's just like the ones we went over at the end of the activity we did on Monday. Just a multiple choice question like one of those. This is another multiple choice question. Now it's a 5 ohm and a 10 ohm in parallel. Okay. 40 is a true false that we will learn about today. 41 is a true false that we will learn about today about magnetism. Okay, basically, well, since you may not know the answer yet, I'll just read what they say. 40 says, science has succeeded in isolating a magnetic pole when a magnet is split so many times it was left with just a north and south, with just a south pole and north pole. Is that a true or false statement? We'll learn today. This is about currently the Earth, the south magnetic pole is near the south. Wait a second. Oh, yeah. Okay, it's a true false. Okay, currently on Earth, the south magnetic pole is near the south geographical pole, and the north magnetic pole is near the north geographical pole. Is that a true or false statement? We'll find out today. And the 42, I got to change. It's the wrong answers are Corky the cockroach, Milburn the mosquito, and Freddy the fly, but you already had that one on the other exam, so I'll change it to something else like what city is the university you're currently going to in? Sacramento, Timbuktu, Moscow, Russia, Beijing, China, something like that. Okay, so I'll modify this. I'm probably going to come in. I came in last Friday, so I can try to keep up with all my classes. But I'll probably be in this Friday. That's probably the day I'm going to mostly work on this. But it'll be along these lines right here. Okay, what is not on there is maybe a little bit less of the earlier stuff and a little bit more of the newer stuff. I got a feeling we had to rush through the newer stuff more last semester than we did this semester. Remember, last semester started off on Zoom. We didn't come back on campus till a few weeks in. Any questions about the exam now? So you got to be here to take it. I think ours is Wednesday at 8 o'clock, but I'll set it up so it'll be open. So it'll be open from 8 o'clock until 11:30. But once you start, you only have 2.5 hours. So if you started at 8 o'clock, you'd have to be finished by 10:30. If you started at 9 o'clock, you'd have to be done by 11:30. If you get start late, then you won't get the full 2.5 hours. Although, I mean, I think the last exam, nobody was here anywhere near the whole time. I think this class emptied out within an hour and 10 minutes or so, I think. Or one of the classes did. Okay, there's no other questions. Okay. I'm going to talk about magnetism, and that'll be it for the semester. So I uploaded the 2 PowerPoints for magnetism already. I saw that they were there in the modules. So I uploaded those a while ago. What happened? Save your work before continuing. I didn't try to close anything. What happened? I don't know what happened. Oh, did I show you guys this? Oh, oops, I showed you guys that if you hold the PVC pipe up here, this guy rolls back and forth. Okay. What the hell? Oh, well, it's the one you already knew wasn't going to be on there anyway. I had closed this. This ticks me off. This thing does not come up where it's supposed to come up to. I had this on my screen. As soon as I turned on the projector, suddenly it switches to a completely different screen. Okay. So magnetism. So a charge in motion gives us a magnetic field. Okay. So an electron in motion gives us an electromagnetic field. That's why they call it the electromagnetic field. If it's just an electron sitting there like we have for static friction, then there's not a magnetic field. There's just an electric field. But most electrons are in motion, okay? They're moving somehow. And as a result, that leads to also a magnetic field that's tied to that electron. Electrons are charged particles. When electrons, okay, now just a bunch of random pictures come up here, but not up there. I don't understand why whoever wrote the software for this, why they couldn't do a better job of that. Electrons are charged particles. When electrons flow in a current, they are in motion and generate a magnetic field. Electrons are also in motion as they orbit the nucleus and as they spin on their axis. So for magnets, it's mostly the electron spinning on its axis that leads to the magnetic field. Okay, this is what I'm going to do. This is different material. You can see which ones are magnet, which ones are not be. Jump back. All I want is a bar. This got a horseshoe magnet, so that's not what I want right now. Here I have no idea where it is. Oh, here are our sheets. I went big one last night. You're gonna get good as these. And instead of making a sheet of this stuff, I should have gone down and got a bar bag. We have a ton of the bar bags. Bar magnet, it's all I want. Okay, we got these. So what I made last night, I did these made. Instead of spending time doing that, I should have spent time. I just assumed we had bar backs there. I just assumed I go back there and find one right away. Have I seen one up here? Ah, we're down to one. I don't know what happened to the others. Maybe it's a good thing I grabbed that one and put it up here because somebody may have gone back and rated us for some other class. That happens, unfortunately. Okay, so here's a bar magnet. So inside of this, there's electrons moving around, and that causes a magnetic field. There's electrons orbiting their nucleus. That causes an electric field because they're in motion. There's also they're spinning on their axis, and that, for some reason, I don't quite understand why, that is the leading contributor to the magnetic field produced by a bar magnet. Okay, so in magnetized materials, it is the spin of the electron that contribute the most to the resulting magnetic field. Magnetized materials have a north pole and a south pole. Just like electrostatics, like charges repel and unlike charges attract. Like poles repel and unlike poles attract. So certain cultures have known about magnetism since before recorded history. Why? Because there are things called lodestones, for example, that are naturally magnetized. And they would have seen these things being attracted to one another. So it must have seemed like magic to have two objects get close to each other and attract to each other. Naturally occurring lodestone attracts iron. This is how people in the ancient world first discovered magnetism. Pieces of lodestone could be shaped to easily align with the Earth's magnetic field, making navigation more accurate. So that's how they could see, wait a second, we take this little piece of lodestone and we let it spin on its own, set it up so it can rotate on its own. One side will face one direction and the other side will face the other direction, and it's consistent. It's always that side facing that direction. So that tells us which way north is, okay? I mean, they know which way the sun comes up and which way the sun goes down. Where would it be here? Oh, it'd be this way. Sun would come up over there and go down over there. So that means that must be north that way. So magnets are strongly attracted to most unmagnetized materials. Aluminum is a noticeable exception. Okay, you can't go out with this big, huge bar magnet along the road and pick up all the aluminum cans with it because aluminum won't be attracted to it. Lodestone attracting iron is how magnetism was first discovered, possibly thousands of years ago. Magnets can be attracted or repelled by other magnets. Magnets have a north and a south pole. Like poles attract, unlike poles, like poles repel, unlike poles attract. North repels north, but attracts south. South repels south, but attracts north. So now here's the Earth. On the old exams, you guys would have to draw a picture like this and draw all the field lines coming out of it. But here's the Earth. And we can model the magnetic field of the Earth as though it were a bar magnet. like this guy right here that I already lost again. Okay, now normally the red side is the north side of this guy. They sometimes they get flipped around, so I don't know. But right now, this would be the north geographical pole up here. North geographical pole here. This would be the south geographical pole. And this is the axis that the Earth rotates on, like this. That's the axis of rotation of the Earth. Now, it turns out at this time, 2022, the year 2022, the south magnetic pole is actually up here near the north geographical pole, and the north geographical pole is the north magnetic pole is actually down here near the south geographical pole. So it's like this. So here's like we could have it like this. This is the north magnetic pole. And up here is the south magnetic pole near the north geographical pole. Now that switches every, I don't know, something like every 30,000 years. We don't know why. We don't know why. How do we know it's switched? Because lava rock, a volcano erupts, sends lava rock down there. Lava rock's full of iron and stuff like that. It solidifies. We can go back and look at lava rock that we know formed so many years ago and see which way did it align in the current magnetic field of the Earth at the time. We can see that we go back so far, the lava rock must have solidified in a magnetic field in which north magnetic was near north geographic. Then we go back further and say, oh, at that time when it solidified, south magnetic was near north geographic. So we can go back and see over time how this is swapped. We don't know why it swaps, but it does. And it moves around. Every year, the Geological Society, which I guess they got a big presence over in that building over there, the U.S. Geological Society. They send people up to see where is the south magnetic pole now. I don't know if they go down, you probably do. Go down and see where is the north magnetic pole now, okay? Can't just walk around with the compass, right? Because, hey, down here in Sacramento works great. It's gonna be that direction. The compass needle is gonna point, but it's not pointing towards the north geographical pole, it's pointing towards the south magnetic pole. Okay. So we get up here, you can't do it. It's not going to work. So how do they even discover where the north geographical pole was in the first place? Well, there are certain things you'll observe here that you won't observe anywhere else on the surface of the Earth. Some stuff to do with the rising and the falling of the sun, sunset, sunrise. When does the sun rise? There's things that will only happen up there. But when you take measurements, that wouldn't happen anywhere else on the surface of the Earth. That's how they first found out where this was. Okay, so due to the molten core full of positive iron ions and negative free electrons and the rapid rotation of the Earth, we are surrounded by a strong and vast magnetic field. Now let's take our two nearest neighbors. We are in what's called the Goldilocks orbit, meaning that we are in the perfect orbit, just right. Venus is too close to the sun, or closer to the sun. It's hot. So, but Venus, we think, did develop this molten iron core. See right here in the middle? There's this molten iron core made up of iron ions that have been heavily ionized and electrons. There's charge. The Earth rotates. That's charge in motion, the magnetic field, okay? Free charges, Earth rotates, charge in motion, okay? Now, Venus has this too, we're sure, because Venus is almost the size of the Earth. The problem is a long time ago, 4.6 billion years ago or so, the solar system was a very violent place, collisions left and right. This one collision, something the size of Mars, smashed into Earth caused this to go at an angle. So in other words, sun, should probably use a different color. This red's running out. Sun, that's supposed to be yellow if you can't see it. Earth, right about here. So our axis of rotation would have been perpendicular to the plane of our orbit around the sun. Something smashed into the Earth, and now it's like this. That's why we have seasons. Sun's here. The same thing that smashed into the Earth that causes to spin at an angle relative to the, not perpendicular, but an angle relative to the plane of our orbit around the sun. It's the same thing that caused material to spew out and then go around the Earth and then come together and make the moon. So the moon came from the surface of the Earth, but something smashed into the Earth and spewed it out there. We didn't originally have a moon. Okay, so now Venus, something happened like that to Venus, except it had a drastic, catastrophic effect for Venus. Something smashed into it and it caused Venus's rotation axis or rotation time to go from maybe 1 day, 24 hours like it is on Earth, to 246 days or something like that. I can't remember the exact number. So in other words, you go up outside today at noon, you go up and look, oh, there's the sun right there overhead. Okay, well, if you're on the equator, it's right there overhead. Go back in your house, wait 24 hours, the sun will the sun will go around, or we'll go around the sun, or we'll spin on our axis, and then you come back out 24 hours later, hey, the sun's back up there. So the sun went whoosh, all the way around, it's back up there. Now, if you want to do the same thing on Venus, to go out, look at where the sun is, and then not come out again until the sun's in the same exact place in the sky, it's going to take 240 some odd days. So the motion part, Venus doesn't have the motion part. So it has no detectable magnetic field. Mars, we don't think Mars is much smaller than the Earth and Venus. So it probably solidified in here. It cooled down too fast. Cooled down, and it doesn't have these free electrons. It's all solid all the way through the volume of Mars. Okay, so that means those two planets get bombarded by the solar wind, which is a collection of electrons and protons, mostly electrons. Our solar wind, the solar wind when it comes to Earth, it gets trapped in our magnetic field. That's why we got the northern lights, the electrons accelerating in the magnetic field. So Earth does have a magnetic field. We are very, very fortunate to have a magnetic field. So due to the molten core full of positive ions and negative free electrons and the rapid rotation of the Earth, we are surrounded by a strong and vast magnetic field. One way to model this magnetic field is to think of a giant bar magnet stretching from near the south geographical pole to near the north geographical pole. As of now, though, the south magnetic pole is near the north geographical pole. South magnetic pole, north geographical pole. So that question that I read you on the exam, the way it stands now, that'd be a false statement, because it said that the north geographical pole and the north magnetic pole were near each other. But I could switch that between now and when the Tuesday, Thursdays have to take the class on Tuesday. Okay. This is why the north pole of a compass needle points in the direction of the north geographical pole. It is actually being attracted towards the south magnetic pole. So when you hold up your compass needle, I didn't even see any compasses back here, come to think of it. We've got compasses back here, but I know they were in here when we were down at the 230. Weird happened back. I probably didn't notice it last minute, but it's still back. Got out so fast. Oh, baggie up in the wrong place. Yeah, I didn't move the stuff up here. That happened between also actually 2019 and spring connected 2020. They're gonna have a bunch of little compasses. These are like little cheapies, but so right about that direction should be the north geographical pole. The south magnetic pole should be that direction right there. Okay. Now, there's another question on the exam, and it's getting answered right here. The poles always come in pairs. You can't, in other words, we can isolate a proton, a positive charge. We can isolate an electron, a negative charge. They can be isolated, not tied to each other, not tied to each other. We can't do that with north and south poles. If you break a magnet in half, you get another north and south pair. So here we got this big magnet, south over here, north over here. Break it right there. Oops, we just formed another north-south pair. North-south pair. Break those in half. Oops, another north-south pair, north-south pair. We get all the way down to the atom, the nucleus. It also has a north and south pair. They've never been able to isolate a magnetic pole. They always come in pairs, okay? If someone was able to one day isolate a south all by itself or north all by itself, they'd be winning the Nobel Prize, and they'd probably go down in history. Maybe not up there with Newton and Einstein, but maybe with I don't know, a Maxwell or someone like that. Okay, ferromagnets and electromagnets. Okay, so this is what happens in a material that we magnetized. Again, like I was saying, it's the spin of the electrons. So you've got your atom, you've got your electron orbiting your atom, and usually either we say the electron spin up or the electron could be spin down. And if you ever watch pictures from those conferences of, I don't know, solid state physicists or people like that, they have so many specialties that, they got these different disciplines within physics, just tons of them, and one person doesn't really know what the other people in the other discipline are doing unless they read their papers. But you see them doing stuff like this. That means electron to spin up, electron to spin down. They'll be doing this. But what are they doing? What is that? Some kind of gang symbol? No, it's a physicist talking about electrons having spin up or spin down. So what we want to do is have them all have spins together. Then they'll add to the magnet. See, if you had these two electrons doing this, spin up and spin down, then the magnetic field cancels. No net magnetic field. Do this up, they're going to add. Now we get a net magnetic field. We've got these little domains. So the way this domain is, the electrons are spinning such that north is up here, the south is down here. Here, north is over here, south is over here. Here, north, see, they're not going to add up. Like that one's going this way, this one's going the opposite way. Those two cancel each other out. So we start rubbing it with a magnet or putting it in a very strong magnetic field, and it'll start to line up more and more. So the north will be kind of, see, that one's still off. These guys are kind of going in the same direction, a little bit different there. Then finally we get this. Now we've got our magnet. This would be the north side of the magnet. This would be the south side of the magnet. So materials such as iron have small domains where the spin of the electrons will create a net magnetic field in that domain, but the spin of the electrons in the next domain may generate a magnetic field in a completely different direction. An external magnetic field can cause the domains to line up to give a more of a net magnetic field. Heating the material, then cooling it, can then bring about a permanent magnet with the domains all contributing to a net magnetic field. Okay, then we have this situation here. So this, okay, by controlling the current, we can turn the magnetic field off and on. So this is called, it's like, what's it called? Soft iron or something like that. It's only becomes magnetized when there's a current put around it, and a current causes a magnetic field. By controlling the current, we can turn the magnetic field on and off. Electromagnets are magnets when the current flows, but are no longer magnets once the flow of current is turned off. That's how those big, huge wrecking yards, you can see that big, huge thing come down, go on top of a car, pick the car up, and then moves it over to a pile someplace, wants to drop it, just turns so it comes down, turns the current on, and then it picks the car up, moves it over here. It's got a big, huge magnet, turns the current off. The magnet is not a magnet anymore, and then the car will fall right into the pile. In scrap metal yards or car wrecking yards, the electromagnet can be used to pick up metal when the magnet is on, and when you want to drop the metal, simply cut the current to turn off the magnetic force. Okay, here we have this situation. So, I mean, we don't really, this is a coil. The whole idea is the coil and the magnet give us the same thing. Now that I found those guys, so I made one of these last night, but it leaks iron filings. This was nice and secure. So there we have Uh-oh. Why is that like that? What is going on? Didn't I? Maybe I never seen this before. That thing is that dark that it looks like that? Yeah. I don't know if it'd be much improved over there because this is white too. I don't know. So you got these iron filings in there. See the iron filings? So they're not magnetized, but what they will do is they will line themselves in the magnetic field we put there. So I take this magnet. It's not going to show up very well. Let me get the one I made last night. Get that to me. A little clear, maybe. I don't. This was not that bad before. I don't know if this is a different thing or what. Okay, way better. I'm glad I made it now. Okay, so there's your iron filings. I'm trying to shake them up. Okay, so now let me take the bar magnet and just drop it on there and see what they did. See how they're going off like this, kind of like we have in this picture here. Okay, obviously nothing we do in the lab is ever as impressive as the pictures they take. So some photographer may have sat there for an hour doing this until they got it exactly right so they could take a picture of it. We're just kind of, let's see, it's coming off like this. You can see them at the end. But move it around. See how they kind of move with it? So let me put it like this. So you can kind of see them doing this. They should be coming off. So there's some circular motion right there. So they should be coming off. And if it was strong enough, we'd see it coming way out here, like these guys. See how it's coming like this? So this is, the question would be, when we drop a bar magnet on a transparency that has iron filings in it, the iron filings do which of the following? Okay, they align themselves parallel to the magnetic field. The other possible answers were they align themselves perpendicular to the magnetic field. No, they don't. This is the magnetic field. They are parallel to the magnetic field lines. So these guys are parallel to it. The other ones would be they're attracted to the magnet. They're not attracted to the magnet. Okay, they're not going towards the magnet. They're just aligning themselves in the magnetic field lines. And then I think the last one was iron cannot be magnetized, so it won't react at all, which is false. Or iron does not react to, iron is like aluminum. It doesn't react to a magnetic field, which is false. Okay, here's that. So here's what's supposed to happen in the picture. It's supposed to be doing west, north, and south. Magnetic field lines are doing this. So they'd be going this direction. They'd be going away from north and towards south. Like we saw on the picture right before. Or wait. Oh, not right before, way back here. Where was it? Oh, was it here? Oh, it's not the other way. That one's showing it go from south to north. Oh, I might have this backwards. These are supposed to go the other way. Well, I have these backwards, I guess. Doesn't matter. You're not going to be asked about it, because I couldn't remember anyway. Okay, when we used the projector to look at how the iron filings align themselves in the plastic sheet when the bar magnet was placed on them, we found that, oh, this is an example. I gave them what the question was going to be on the exam before the exam, but they didn't have this on the exam anyway. The two they had was scientists have been able to isolate a magnetic pole. That's false. They always come in pairs, north and south. And the other one probably said in our room, the north side of our compass needle will point in what direction. Okay, we'll get to that here in a second. You see all the iron filings were repelled by the magnet. Well, that's wrong. The filings align themselves perpendicular, no, parallel. So C, the filings align themselves parallel to the magnetic field. That's the one you'd want to pick. The filings didn't align themselves in the field at all because they are not magnets. Well, they're not magnets. That part is true unless we magnetize them, but they still react to the magnetic field. Okay, this is written for, this is another sample problem. A flat square magnet floating on a lid in water is allowed to align itself in the Earth's magnetic field. One side of the magnet is south pole of the magnet and is blue, and the other side is the north pole of the magnet and is green. Okay, this is one that you would have to do. This wasn't multiple choice. This is one you actually had to get up and do. Predict which way the two sides, the blue and the green, will be facing when it comes to a stop. In other words, which side will face towards the blackboard. Okay, this was written for room 242. At 242, the blackboard would be there. Okay, but now, see, okay, then here, let's make sure. It's always good. I mean, in this day and age, the world is so incredible. Okay, true crime garage, but I want this. Okay, this is Sequoia Hall right here. Okay, we are in this corner of Sequoia Hall. Everybody agree? We're one floor down from what we're looking at, but we're on the fourth floor. There's a fifth floor, but this is our room right here, right? This right here, that's the window right there, right? Everybody agree? Everybody's pointing to themselves. So let's see, which way is this way? So there's Chico, there's Reading. So that way is towards Chico and Reading. That way is north. And we are north of Highway 50. Oh no, what happened? How come it doesn't go in where you were? Dadgummit. Where did I go in at? Auburn. There's Auburn. Oh, we're way up into the Sierra. How come it didn't go back to where I was? All right, let me go way out. We're way north of Sacramento. There's Highway 50. So I need a street. Folsom, but that doesn't help me. You guys know where we are? Oh, there's Hal. So Hal, we go College Town, and then we go in here. Nope, we don't go there. We're not even on the right side of the American River, are we? Oh, look, there's a football stadium. That's housing. I'm lost again. Oh, there's the American River. Oh, okay, wait. How can I get? Oh, there's the Hornet Bookstore. Good. So here we are. We are there. Then here's Highway 50. So we are north of 50. 50's over there. So anyway, there's my argument. That way is north. Okay, so now what we can do, let me take this down. We don't need this. So what we'll do is we'll take this guy here. And I'm only putting him up here so people can see what I'm doing. We'll get some water. Oh, I'm glad I came over here. That reminds me. Yesterday we found out that if you use the charged PVC pipe near this stream of water, you can see it move better than you can on that one. I don't know what the difference is. Oh, I got to be careful here. I don't want to spill water on my computer. Well, there is a document cap. I don't know how to set it up though. I don't know how to set up the document cap. They just brought it up because another teacher who doesn't even teach in this room anymore and won't be this semester or next semester. So I should not. So we get a lid. I'm going to float the lid. The lid is floating in the water. Take that little magnet. It's got a blue side and a green side. Put it like just in there. Probably want to keep it away from the side. Let's see, this is, oh, you know what? It's hitting the bottom. I didn't put enough water into it. Oh, that was floating. Okay, so now the blue side is pointing over there. Blue side's coming towards me. Blue side's pointing that direction now. Now the green side's pointing that direction. I don't want the green side to go back over here a little bit. It's slowly doing it. Okay, so the green side is pointing in that direction. That means the green side is being attracted towards the south magnetic pole of the Earth, near the north geographical pole. So that way would be the north geographical pole, south magnetic pole. See if we can mess it up again and wait about 5 minutes and it'll still hopefully do the same thing. If it's not hitting the bottom, I think it's hitting the bottom. I didn't put enough water in. Okay, the green side's pointing that way. It looks like it's going to stay there. I turn it all the way around. Green side's pointing that direction. Hitting the bottom again. It hits the bottom, it's no good. Green side's pointing that direction. Slowly turning. Let me put some more water in there. This guy. Oops. That's more than enough. Okay, it'll work better now. The green's pointing towards me now. Now the green's pointing that direction. Now it's coming back towards me. Get it out of the corner. Green's pointing towards me. It was pointing over there. Now the green is pointing over there. It'll probably overshoot it, so now it's pointing over there. But it should come to a stop if it doesn't hit the side.
Because it's not flat.
Yeah, it could be. Now the green's pointing this way. Now it's pointing towards me. Now stop rotating. Now it's pointing in that direction. Now it's pointing where it's supposed to be pointing, but it'll probably overshoot it before it's the side. Anyway, we could be pretty sure it's the green side that's being attracted in that direction. Okay, are there any questions about anything? Take roll, and then you guys can hang around or do whatever you want. See, now you got to be here in class on Wednesday to take the exam. Okay, you got to be here. So okay, I got to do two things. I got to stop the share. I should probably also stop recording because we don't need other people to know what we're talking about now.